Hi, uh, good morning, and thank you everyone for coming up to this presentation at this very early morning. So I'm Weizhong. I'm Weizhong from the University of Hong Kong. My supervisor is Joshua Ho, and my co-supervisor, Dr. Yuanhua Huang. So I'm very excited to be here, share our recent works with you. In this talk, we will share about how to build more generalizable multitasking learning and how to use this model to extract some meaningful regulatory sequence motif. So as we all know, the genetic information is stored in the DNA and it was passed to the RNA through the transcription. And then it was passed from RNA to protein through the translation. While the regulation of transcription is more studied, I would say, the regulation at the translation level is less understood. So to be clear, today's talk we will focus on the regulation of translation, which is at this part. So here on the right, we're showing you a structure of a mature mRNA. So at the very beginning, from the 5' end, we have a 5' untranslated regions. And then it follows with a CDS region, which encoded protein. And finally, it ends with the 3' UTR. So we know that the canonical translation process starts with a ribosome scanning through the 5' UTR, and it was until it detects a stop codon, then you start to initiate the translation. So we already know that it will first go through the 5' UTR, and the sequence of this part is going to affect the efficiency of the translation, or we call the activity. But we still don't know how the sequence influences the activities. So the mapping from these two spaces is still unknown. And furthermore, we also don't know what's inside the sequence. Are there some determinant that means more important part than the other that can regulate the events? So to measure the activity, several methods has been developed. So there are massive parallel reporter assay, MPRA, ribosome profiling, and facts-coupled sequencing. Each of these methods have its own characteristic and are describing different facets of the translation system. So massive parallel reporter assay has the biggest scalability. It can measure up to millions of sequences at the same time, and also have a fixed coding region, usually GFP, which makes it very clean. However, it can only measure some exogenous sequence. So what I mean by that is that you can only measure a UTR that was transfected later into the cell, but not original in the cells. And it can also capture the influence of different lengths of 5' UTR. And ribosome profiling stands for a more earlier version. And although the scale it's not that high, but it's just at the genome scale. So it can, in theory, measure up to the number of your transcripts of UTR. And the coding region is changing from sequence by sequence as it depends on the gene. And most importantly, it's actually measuring the endogenous translation systems. And with this technology, we are now able to build deep learning methods that map from the sequence to predictions. So currently, deep learning methods are very widely used to discover some regulatory patterns during the modeling. And the underlying idea of that is that in order for the model to make prediction, it must capture some meaningful patterns inside the models. So in the case of face recognition, we know that in the lower layer of CNN, it's just detecting some very simple texture like different ages. And this basic patterns was assembled into high-level or more meaningful part of the face. And then the other part of the model would take these detected patterns to make the, predictions. And similar in modeling the UTR sequences, we can also observe that in the lower layer of CNN, the model is detecting some very simple patterns like nearly chimer, and these simple patterns was example in higher layer into more complex high-level motifs that are relevant to translation. And finally, the MLP or dense layer of other part of the model would take use of these detecting motifs and do the prediction for you. So far seems perfect, but Carolus, they found it out that there was a problem in generalizing the detected motifs. So they fit CNN models on the very large and clean massive parallel assay and use attribute methods to aggregate some of the sequence motif. And when they're ready to examine that motifs and a smaller n, what we have mentioned endogenous sequence, they find out that the UTRs have and don't have these motifs. They absolutely have no difference at all. And this means that these motifs are not informative. So we're reasoning that maybe they're capturing some technical error, or this is just a shortcut learning. So from here, we formulate our questions. So first, we want to know how can we effectively integrate the large sequence context bring by those massive parallel reported assay and use it to inform the prediction in the more smaller but noisy ribosome profiling data. And then we want to know how can we extract more meaningful, or we say genuine regulatory motifs by making this meaningful prediction. And finally, we ask the question, once you have detected this motif, how can you use them to finally come up with the translation rates? So these three questions comes with three different levels. So one is how to make better prediction, and the second tells me how can we use the internal hidden variable to capture meaningful motif, and finally how to use these capture patterns to reasoning. So to our methods, we call MTtrans, Multitask Learning for Translation Prediction. It's just a simple multitask learning methods. But our multitask learning method is iterative, and there is a simple idea behind that. So we treat each data set or treat each techniques as different tasks. And it is iterative by that in each mini batch, we sample data from different techniques. And you notice that each data set will only update its own task-specific tower. However, the same shadow encoder was used for all the techniques. So by doing that, we're hoping that the same set of motif can be captured by the CNN that was working for all different techniques. So hoping that our assumption is that this same set of motif are more likely to be generating regulatory patterns. And then we test that out in 4 massive parallel reporter assays. So there are 4 data sets, so with very different sequence design. Some are random sequence with fixed length or varying length. Some are natural human UTRs with also fixed length and varying length. Because we're doing simple regression problem, the accuracy can be just measured by the R-square. So we find it out that our MTtrans method can outperform all the baseline methods. And we also additionally construct a baseline called mixing. So mixing is just the same model architecture, but it's simple task trained on a large data set, which just simply merge all the 4 data sets together. And we noticed that for this mixing, there's a huge performance drop in this fixed length natural human sequences. However, our multitask learning methods did not experience with this pain. So we reasoned that there was conflict between each task. And if you just simply merge the data together, this conflict will actually hurt the prediction. However, if you give some levels of sharedness and give some levels of independence, this conflict can be solved. And this is how our model can outperform and capture task-specific patterns at the same time remain the most commonest as possible. So we also argue that if this set of patterns is capturing some generally biological patterns, then it should be able to generalize to some biological relevant data sets. So holding that, we want to use transfer learning with fixed encoder to evaluate how generalizable are our common motifs. So to do that, we just use the model we showed and fix the parameter and transfer it into a yeast MRNA data sets. And we find it out that MTtrans is much more accurate than the other state-of-the-art methods, and it was so close to the method that was trained from stretch. That means this stretch model is totally adapted to the translation pattern of yeast. However, the MTtrans we capture by gathering different just human data sets are able to reach that. So this level of improvement indicates that we actually capture some evolutionary conserved patterns. And moreover, what we have just talked about are mRNA data sets. Although they are large and clean, they can only measure the exogenous sequence. And to understand how the gene was translated, we want to go back to the ribosome profiling. So here we show that we train new model called 3R, which is just using 3 ribosome profiling data, or we can also co-optimize the model together using ribosome profiling and massive parallel assay data. This gives us to 3R2M model. So in this performance plot, we find it out that the much of the performance gains was contributed by just using more ribosome profiling data, as shown in this green color. However, we can further improve this performance by using more large data set bring by the massive parallel assay data. So this result have shown that we have kind of resolved the problem that correlates have encountered, that the model trained on large data set is not working in the endogenous one. So here, using multitask method, we're kind of solving the large exogenous sequence and together to string up with the endogenous sequence. So we have now demonstrated that this method is quite useful in capturing that useful sequence pattern. And we really want to know what are these shared patterns. So we just simply do a dimension reduction on the feature map, and each dot in this plot is a CNN kernel. And for each kernel, we can also use maximum activation to transform it into a sequence motif. So here we can see that negative motif and positive motif are actually displayed in different part of the space. And we also find out that motifs are biologically meaningful. Not only do we find out that there is some diamond-shaped motif that are very similar to the binding sites of RNA binding protein, but we also find some of the already known patterns like AUG, the start codon or upstream stop codon, or some of the stop codon here, which are known to regulate the translation. And finally, we can use experiment to validate that these capture motifs are really biological meaningful. So we designed a new FACSIC dataset library, and from here, we only take the least translated and most translated sequence to formulate 2 classes. And then we use this explain motif to train a simple random forest or logistic route algorithm, which is quite simple machine learning methods. And it is a classification problem. So we found it out that just using this motif without any deep learning, we can outperform the state-of-art transfer ones. Of course, if you just transfer MTtrans, you always get the best result on this classification. So we want to use this experiment to demonstrate that we don't just rely on the deep learning, but just using the pattern detected by our methods. It was already very informative. So far, we're just talking about the feature detection. We still don't talk about this, how the motifs are used to make up the final predictions. And to discuss that, let's have a detailed look at their inner working. So CNN scans through the sequence and gives us the feature map, which is the activation of different patterns. And then the GRU layer in the task-specific tower would take up the kernel activation at each position and store this in the memory, which is the hidden state. And it was until the last memory state that it will capture all the patterns already captured in the whole sequence. And then we will transform this memory using a dense layer into translation rate. And this is how we do the backpropagation. However, if you think about this, the dense layer is actually a mapping function that maps from your GRU memory space into a translation activity. So we're thinking about why not also transform this intermediate GRU memory into a translation-related score. And this is our rewinding techniques. And this is actually a very simple feed-forward method that can interpret your intermediate incomplete GRU memory, because the only one at the last one can have seen the whole sequence. However, the memory in the middle that having look at the partial sequence. So what we are going to do with this is that if you can transform the intermediate ones, we can have a trajectory along the way from 5'n to 3'n to tell you how translation is established step by step. Applying these GRU rewinding methods on highly translated sequence and lowly translated sequence, we find out there is a distinct pattern between them. So this highly positive sequence, they have nearly monotudinal increasing trend. However, in this low translated sequence, we find out there is some sudden transition that decrease your translation rates. So we're very interested in what's happening here to make up this transition. So we sample at the change point of the CNN activation and also sample from the positive sequence as the background. So doing hierarchical clustering, we find it out that there is a set of CNN kernels that are specifically enriched in this change point. And when we visualize them in the UMap we just showed, we found out that they're mostly enriched in this negative region. So this is telling us, indeed, these motifs are actually highly negative, and the change point that we reconstructed by our method is indeed meaningful. So here I would like to give a conclusion. So using our MTtrans is not only giving you a robust prediction, and also the shared encoder captures some very meaningful motifs. And using this motif, we can further validate it in our in-house FACSIC data set. And then finally, we introduce a GRU interpretation networks called GRU rewinding that can help us to locate important locations. So finally, I would like to acknowledge my supervisor, Dr. Joshua and Yuanhua Huang, for their support, and our collaborators for kindly providing the FACSIC dataset. And we also like to thank the contributor and recon committee for improving our works. I would like to take a question if there are any. Thank you.